Next speaker we have is coming from one of the world's leading solar research institutes. We're very happy to have with us Paul Gebhardt, who's the head of team module analytics at Fraunhofer ISE. And he will talk about analysis of backsheet failure. Paul, the floor is yours.
Thank you, Michael, for having me, and thanks for the opportunity to talk about backsheet failures and how we analyze them at our lab. So before I get into detail with different backsheets and analysis techniques, I want to quickly talk about what we do in our lab in the Department of PV Module Characterization and Reliability at Fraunhofer ISE. So on the one hand, we operate two accredited test laboratories. One is the color PV modules, which does, as the name suggests, a calibration of modules with a very low measurement uncertainty, and also performs additional measurements, for example, for the energy rating. And we also operate the test lab PV modules, which does certification of PV modules according to the standards IC 61215 and 61730 mainly, but also extended characterization, for example, for module qualification or customer qualification, things like that. And on the other hand, we have the group degradation analysis and modeling, where we look at the degradation mechanisms themselves, and important is also the material degradation. So for example, encapsulant polymer materials like the backsheets. And we also do damage assessment as a service. So root cause analysis and similar projects. And I will talk about our findings from these projects in a bit. Additionally to this, we also try to model these degradation mechanisms. So we identify how exactly the mechanisms work and what drives them in terms of environmental stress as well as material properties. We look at different load and acceleration factors, for example, in different climates or different applications. And one example would be the modeling of moisture ingress depending on the climate and the material properties.
Paul, are you showing already a PPT or not?
Oh, yes, I am. Sorry for that. Yeah, good. Thanks for giving me this comment on a second slide. That would have been
might be just the intro and
thanks. So you should see it now.
Yep.
Okay. Sorry for that. I was talking about the accredited test labs on the left and the degradation analysis on the right side. So additionally to this, we also develop test methods and measurement methods that go beyond the normal standard tests, for example, for qualification in special climates or special applications like floating PV or special environmental conditions. And we also develop new analysis techniques for special failures or similar things. So what I want to talk today about is lessons we learned in our damage assessment as a service projects. Then I want to introduce some backsheet analysis techniques that we use in our everyday work in these projects to find out which backsheets are critical, how they degrade exactly, which modules on the field need to be replaced, for example, things like that. And then I'll finish with a brief outlook, commenting on the current materials, also some things that we heard about, the currently very relevant materials. So let me start with our findings. So last year we accumulated what we learned from a lot of failure analysis projects in a publication. So we saw that we had tested almost 300 modules from 26 different power plants, and we saw a wide range of backsheet products and material combinations in these projects. So some of them are listed here, the most frequent ones in our lab. Of course, this is not representative to the market, because these modules come from a long range of time, sometimes almost 10 years ago. And if we look at the failing materials, they were mostly comprised of these three material combinations. So there is this AAA, which is quite famous. It's the combination of 3 layers of polyamide. Many of you know this material probably because it has been a big problem for the industry. I have brought some examples of cross sections of this material, and AAA is the middle one. So you basically see one large polyamide layer with glass fibers in the middle. The standard cross section of a backsheet looks maybe similar to this. So this is a backsheet that has 2 PVF layers and a PT core. This is the legacy material, the TPT material that, as we have seen, has around 10% market share at the moment. This is the non-transparent version, of course. So coming back to the problematic backsheet that we observed, another one was this rather special configuration of a fluoropolymeric coating, then a PET layer, and then a polypropylene layer. And it was this polypropylene layer, as you will see on some of the next slides, that were not very well protected against UV radiation, and were then decomposing upon longer times of UV irradiation. So of course, these findings, I want to stress again, this is not representative to the market. In our lab, we often only see the bad results, and there are, of course, a lot of good products on the market. But one thing that we saw is that the exact combination of materials is very crucial, not just one backsheet type, but also the combination with different EVAs. And we also saw that a lot of module types contain different backsheets or EVAs even on one power plant. So it often happens that only part of the power plants develop a certain backsheet failure, and it is one of our tasks then to identify exactly which modules are critically damaged. So talking about PV module backsheet failures in general, I want to quickly give an overview of what we most frequently see, and that's external cracks, as you can see in this photograph here. So these cracks are along the cell edge, which means they are most likely connected to UV irradiation. We can have internal cracks. This is an extreme example where one layer inside the backsheet is damaged, but the outer layers are intact. So it's not really possible to see this failure with the eye only. Then we have delamination, which is also an internal failure, where we have a detachment of the backsheet from the EVA. This is a cross-section micrograph. And then we have chalking. So this is a white powder on the backsheet rear. The powder consists typically of titanium dioxide pigments. And this can be an early warning sign for material degradation. And it's also a very frequent thing that we see in AAA backsheet degradation. In general, degradation of backsheet can lead to insulation loss because one of the backsheet's main function is the electrical insulation for safety. In first approximation, the degradation does not change the module output power, but it can trigger secondary degradation mechanisms due to moisture ingress, and this can cause corrosion of the cells or cell connectors, depending on what exactly is the cell technology that is used in these modules. And of course, a low insulation can also lead to inverter outages, and thereby also remove the yield or lessen the yield of the power plant. Therefore, an early detection and a very good understanding of the processes in the power plants is necessary as soon there's some signs of backsheet degradation. So it's very important to define a suitable mitigation procedure and to define which modules are really relevant for this backsheet degradation. And we also need to qualify new backsheet products. We have seen today that a lot of the products that are very relevant on the market today are quite new. And they need to be qualified, of course, to avoid disasters like the AAA backsheet, for example. So there are several test protocols. We just heard some approaches from PV Evolution Lab, and there's also the famous mass cycle from DuPont. There are some variants, for example, one variant that we developed with them to shorten the test procedure a bit. Then there's our own multi-cycle test that features a combination of UV and damp heat conditions at the same time simultaneously. Then there are other tests like CAST, for example, from NREL, which works well on small size modules, and some others. I don't want to go into detail about this, but yeah, there are, of course, test procedures. So now coming to the analysis and test approaches. So one thing I want to mention is the wet leakage test according to ISE 61215-2. It is actually in the context of certification valid for new modules right after some accelerated aging tests, and this is not officially designed, the standard for evaluation of modules that have been exposed in the field. However, the criteria for safety is, in our opinion, still applicable in this case, and we use it to determine the safety of the modules in the field. However, when we do this test according to standard with a standard wetting time that is very short, we see not always the results that reproduce the findings from the field. And I have brought one example of 5 modules. According to the normal wet leakage test, according to standard, they showed insulation resistance around 300 mega ohms, but a longer wetting time before the test. So immersing the modules in water before measuring the insulation between cell circuit and ground potential. This led to a strong decrease of the values of the insulation resistance, and this was actually more representative to the findings in the field. Therefore, we concluded that it's necessary to extend this wetting time, and one reason for this might be that the modules simply dry out, for example, in the storage or the transport time right before the test that we perform in our lab. Then I want to start with some of the analysis techniques. So one very simple one that can even be used on the field to detect some of the failures, for example, internal cracks, is what we call the illumination test. So this method is non-destructive, which is nice. And the method is just to illuminate the module, for example, with a flashlight, but in some installations, even the sun irradiation is enough. And looking across this illumination from the other side of the module, cracks can be visualized, as you can see here on the right side, even when the backsheet seems totally intact from the outside. This can be very helpful to identify modules, for example, for further tests in the laboratory. However, there are some limitations to this method. For example, only the cell gaps can be investigated, and the exact damage layer and further information, of course, cannot be obtained from this method, but it's a very good starting point. And then when we go for more sophisticated testing in our lab, for example, FTIR in general, infrared spectroscopy is a very important tool to identify the materials that are present in the backsheet, and also to identify different backsheets and maybe some starting degradation already. There is, for example, a near infrared spectroscopy, which also is connected to a database to identify different backsheet materials in general. But what I want to talk about is the exact determination of the different backsheet layers. So if we have a module from a module buyer and they are not sure if the backsheet is really the one that's listed on the data sheet, for example, or that was agreed on during the purchase process, we need to check the material for its components, and sometimes it's not easy to separate the different backsheet layers. They can be very small, especially now with materials like CPC. I showed you this image of one backsheet that was separated manually, and it can happen that the adhesion is maybe too strong to separate the layers completely. So one possibility to overcome these limitations is FTIR microscopy, where we actually just look at the cross-section itself. So such a backsheet cross-section can be obtained by really cutting out a piece of the backsheet, embedding it in epoxy resin, and grinding and polishing it, so you get a nice view from the cross section. And in FTIR microscopy, you can actually select areas for a spectral measurement, so you can actually directly select the specific layers. So I brought some examples. Where you basically see some spectrum, and with some material knowledge, you can identify this is a backsheet that consists of two polyamide layers with a PET layer in the center. And this works in many cases quite well. Another very interesting method is scanning acoustic microscopy. It's nice because it's a non-destructive method, and it can be, this image is on a small size module, but we can also do it in a similar way on full size modules. The concept consists of a transducer, which you see here, which scans over the PV module, which is put in a coupling fluid, which can be typically water. And this transducer emits ultrasonic waves, which penetrate the module and reflect at every interface due to the different acoustic impedance of the materials. And you obtain such a reflectogram with some experience. You can see the different interfaces. For example, the backsheet, different backsheet layers are these signals here. Then we have the backsheet EVA interface, and then we have the EVA cell interface. And by scanning a larger area, we can collect a lot of these reflectograms for a large area of the module, and therefore also gain information about the spatial resolution of some backsheet failures. For example, here on the left side, you see one of these internal cracks, internally cracked backsheets. So the backsheet looks very good from the outside if you look at it simply with the naked eye. But using scanning acoustic microscopy, we can detect these internal cracks, and this area between the cells can also be detected. So behind the cells that you see here, so these are monocrystalline cells. Behind the cells, there are no cracks, but in between the cells, there are a lot of cracks in some specific layers, which correspond again to this damaged PP layer, polypropylene layer that I mentioned in the beginning. And using more sophisticated scanning techniques like line scans, we can even identify the different layers and exactly the cracked layer in the material stack completely without destroying these modules. All right, I want to comment on PVDF simply because it has been an extremely relevant product on the market in the last years. So of course, we all know it's a fluoropolymer. It was introduced as a cost-effective alternative to PVF, the conventional Tedlar material, and products on the market or backsheets that we see in our lab consists of different structures. They can be so the outer layer is usually PVDF, but the inner layer can be a fluoropolymeric coating. It can be PVDF just as well, or it can be some E layers or some POE or EVA blend or some similar material. And additionally to this, the PVDF layer itself can have very different characteristics. So it can consist of an acrylate blend. It can contain various amounts of titanium dioxide filler as pigments. It can have different crystalline phases, and it can also have different layer combinations. So there is this very recent publication that shows that some of the PVDF layers have an acrylate blend on the core, and then two more pure PVDF layers on the edges, of course, also with titanium filler. So we have a lot of different layer structures and a lot of different actually material properties. So yeah, PVDF backsheet is not one type of backsheet, but it has a lot of, it can have a very different amount of, very different quality. Of course, there are also several different manufacturers who produce these materials. Therefore, yeah, looking at this material is critical. There are already some publications about degradation and cracking of these backsheets indoor and outdoor from a large, for example, from a large field survey, which is of course not 100% representative to the installations around the world, but it's the largest we know. And they found that 7% of the PVDF backsheets were cracking in 2017. There is already some information about the degradation mechanism, and yeah, we are doing further research to get information and knowledge about this material. But qualification or analysis of this is a relevant topic for us. So I want to summarize and give a brief outlook. So as I said, from the procedure point of view, we often see different bill of materials, BOM, in PV modules of the same type. So this is a very relevant point for us. Wet leakage test procedures could be adapted in some cases. I showed you some of the characterization methods that we use, of which some are non-destructive, which is always nice if we work on someone else's modules. And just to give a nice a short outlook on what we already heard today. So as we've seen, the market is very dynamic at the moment, a lot of change in products and material combinations. And if we talk about the CPC backsheet, which has now more than 50% market share, this is a material that we have not much knowledge about. There's not much openly accessible literature about the material, its properties, and the degradation mechanisms. So for sure, yeah, there needs to be more work on this. And I personally expect that some of these materials might be critical and very good testing and qualification of these materials, especially by third parties, is required to avoid failures and to supply a good good relations to customers and power plant builders like EPCs to avoid these problems. So thanks for your attention, and of course I'm happy to answer any questions if there is still time.
Thanks, Paul. Very nice, very comprehensive overview. I think we're running a little bit late, so it would be great if you could answer questions. There are questions in the chat. If you could take a look at that and answer them
in a
written way. Yeah, that would be nice.